Hello and welcome to Calculus 2. In this video, we are going to take a look at some prerequisites that should be review for the most part, but these are some foundational pieces of knowledge that we should know as we start Calculus 2. This is actually very important material. We want to make sure to be comfortable with the content that's presented here, and we want to make sure that we have a strong foundation as we start Calc 2. So you should have the handouts printed out. You should have this handout and have some paper off to the side as well to take notes in. There's some space here, but this is not nearly enough space to write down all the examples. So you want to make sure to have another notebook where you can write down the fully worked out examples. Stay engaged with the video, have the handout there, and be writing along with me as we work through the problems. I would encourage you as well, since this should be review material for this handout, I would encourage you to try solving each and every problem for this particular handout before we actually work through it together. So go ahead and pause the video when we get to a problem, try it yourself. That'll be really good practice, and then we'll work through the solution together. So it's important to understand that a strong foundation in algebra, trig, and Calc 1 is absolutely essential to doing well in Calculus 2. One of the biggest challenges in Calculus 2 is to be solid in the foundational prerequisite material. So that's what we're going to talk about in this video. We're going to talk about some algebra skills, working with fractions, exponents, doing some expanding and factoring. We're going to talk about some graphs, and here in particular are some important graphs that we want to know. For each and every one of these graphs, we want to be able to draw a rough sketch of what the graph looks like, and we'll practice with that in just a bit. We also should know a little bit about horizontal and vertical shifts, stretches, those sort of modifications to a graph. It's important to know some of the basics of transcendental functions. Transcendental functions are trig functions like sine, cosine, tangent, exponential functions such as e to the x, logarithmic functions like the natural log functions. These are functions that we use a lot in Calculus 2. So we want to be comfortable with working with those, knowing what the graphs look like, knowing some of the certain values. So we want to know this identity in particular. We'll be able to develop some other identities from that. We will use this identity later in an integration technique. We want to know some things about trig notation. So in particular, let's make a little note here. For trig notation, we want to understand that we can represent the power of a trig function, such as sine of x squared. We can represent that as sine squared of x. These are the same thing. This works for any power except when we use the exponent -1. If we use sine to the -1 of x, this does not mean sine of x raised to the -1. Sine of x to the -1 could also be written as 1 divided by sine of x. And for this power of -1, this is a special case where this notation is not appropriate. So sine, this is not sine raised to the -1. This is actually representing the inverse sine function. So the notation that I prefer to use here is actually arcsine. This is the inverse sine function. We could also write down the inverse tangent function, or the arctangent function, with a similar notation. It's tangent, and then we use this -1 exponent, but it does not mean raising to the -1 power. This is not equal to 1 divided by tangent of x. So this special power notation is only appropriate when we are using powers not equal to -1. Along with the trig notation, we want to be comfortable with some important exponential and log values, such as e to the 0, natural log of 1, natural log of e. We'll practice with those in a little bit. We also want to have a strong foundation in Calculus 1 skills. We want to know how to calculate important limits. We want to be really comfortable with derivatives, all the derivative rules, including chain rule, product rule. We see those quite a bit in Calc 2. So we want to be really feeling confident with derivatives, and we'll get some practice with that in as well. And then basic integrals. The start of Calculus 2 is a large focus on integration techniques. So we're going to practice a lot with integrals, but we have to know basic integrals, the fundamental properties of integrals. On Canvas, you will find a list of derivative rules and integral rules. I strongly encourage you to print those out and to practice with them and to know all of those integration and derivative rules by heart. You want to have those really well established so that you can use those rules at any moment for an integral or a derivative problem. Now, let's try working through some examples. Let's start with some algebra practice. We'll work on simplifying expressions that involve fractions and exponents. So for the first problem here, we have two fractions added together, 2/3 plus 5/4. Once again, Please take the time to try these problems yourself before we work through them together. We want to know how to add fractions. Hopefully this is review. This should, we should look at this and say, oh yeah, we remember how to add fractions. We remember how to multiply. Maybe it's been a little while and that's why we're working through the review, but it's important to have this prerequisite knowledge as we start Calculus 2. So how do we add fractions together? The important thing when adding fractions is to find common denominators. So one of the denominators is 3, the other is 4. I have to multiply the first fraction, numerator and denominator, by 4. So I multiply the first fraction by 4, and the second fraction multiply numerator and denominator by 3. So the first fraction simplifies to 8 over 12. The second simplifies to 15 over 12. And now that we have common denominators, we can add. 8 plus 15 is 23. So we have 23 over 12, and that is our answer. When we are multiplying fractions together, we simply multiply the numerators and multiply the denominators. 2 times 5 equals 10, 3 times 4 equals 12. I hope you're working through these problems on your own before we solve them together. I'm hoping this is review and seems pretty straightforward so far. If you feel rusty on any of these problems, you definitely want to make sure to brush up on that particular type of example and make sure that you're really comfortable with the principles and rules that we're using here. Example 3. 3 divided by 1 minus 2/3. Well, first thing we can do is simplify the denominator. So since we're subtracting fractions, I really want to get a common denominator here with the 1. So I'll rewrite the 1 as a 3 over 3. 3/3 minus 2/3. And now I can subtract fractions in the denominator. 3 minus 2 is 1. So I'll have a 1/3 in the denominator. 3 divided by 1/3. Now we're really doing fraction division. 3 over 1 divided by 1 over 3. So we could write this as 3 over 1 divided by 1 over 3. And when we're dividing fractions, we can invert the denominator fraction and multiply. So in the numerator, we have the fraction 3 over 1. In the denominator, we have 1/3. We invert that to be also 3 over 1, and now we can multiply. So when we divide two fractions together, we invert the denominator fraction and then multiply. So our final answer here is 9. As we're working through the problems here, I will mention that a lot of the examples are very similar to simplifications that we'll see later on in the course. These are foundational algebra examples that we'll see later on as we work through calculus examples. Okay, problem 4. 3/5 squared. When we're squaring a fraction like this, we can square the numerator, 3 squared, square the denominator, and simplify 9 over 25. For example 5. We are raising x squared to the third power. When we have an exponent that is then raised to an exponent, the exponents are multiplied together. So this becomes x squared, x to the 2 times 3. X to the 2 times 3. It's not x to the 2 to the 3 power. It's we multiply the exponents together. So if it were 2 to the 3 power, that'd be 8. It is not x to the 8. It is x to the 6. When we have an exponent that is then raised to an exponent, we multiply the exponents together. How about example 6? When we have the same base and different exponents, then we can add the exponents together. This simplifies to be x to the 2 plus 3. And an easy way to see that is to write out x squared as x times x, and then x cubed is x times x times x. And then if we count how many x's we have 1, 2, 3, 4, 5 x's multiplied together. That's x to the 5th. X to the 5th. Where did the 5 come from? It's x to the 2 plus 3. So when we have two of the same bases multiplied together with exponents, we add the exponents together to simplify. So we get x to the 5th. Example 7. Here we have different bases, but we have the same exponent. And since we have the same exponent, we can simplify as xy, all raised to the third power. Example 8 is an important kind of simplification that we'll see fairly often in Calculus 2. Here we have a fraction that we want to simplify, and it's important to notice that there are two terms in the numerator. We can simplify by breaking this fraction into two separate fractions. We can write this as x squared divided by the square root of x minus 1 divided by the square root of x. And I'm going to go ahead and get rid of the radicals in the denominators here. So square root of x is the same as x to the 1/2 power. So we have x squared divided by x to the 1/2 minus 1 divided by x to the 1/2. When we have a fraction with the same base in the numerator and denominator, we can simplify by subtracting the powers. So this first term is going to simplify to x to the 2 minus 1/2. We take the power in the numerator and subtract the power in the denominator. And for the second fraction, when we have a power in the denominator like this, we can simplify by making the power negative. So this is going to be minus x to the negative 1/2. And we can simplify the first a little bit. 2 minus 1/2 is, let's see, 4 halves minus 1/2, that's 3 halves. So we can rewrite this as x to the 3 halves minus x to the negative 1/2. It's important to recognize that this kind of a simplification only works when we have multiple terms in the numerator. For example, if we had a similar looking expression, such as square root of x divided by x squared minus 1, this looks fairly similar, it's just the reciprocal, but this is not equal to square root of x over x squared minus square root of x over 1. We cannot break up a fraction when we have multiple terms in the denominator like this. This sort of a trick only works when we have multiple terms in the numerator. And this is an algebraic simplification that we'll use to help simplify calculus problems later on in the course. Let's solve example 9. We can take the powers in the denominator and bring them up to the numerator by making the powers negative. So we can simplify to have 3x times square root of y. I'm going to write square root of y as y to the 1/2. And now I'll consider the denominator. Instead of x to the 4th times y, I will have x to the negative 4 times y to the negative 1. I'm going to group the x's together. I can do that because it's multiplication. I can rearrange the order if I want. And I'll group the y's together. So we get 3x to the 1 minus 4 times y to the 1/2 minus 1, and this simplifies to 3x to the negative 3, y to the negative 1/2. Next, let's work on some problems involving factoring and expanding. For these examples, we want to simply expand out these expressions. So first we have 3e to the t plus 1 quantity squared. We could simplify if we want by writing this as 3e to the t plus 1 times 3e to the t plus 1. If you can skip this step, it will help with some simplifications. If we can think of expanding straight from this expression, that would be helpful. At this point, though, we can simply FOIL. 3e to the t times 3e to the t becomes 9e to the t squared, which is e to the 2t. Notice here that e to the 2t is from e to the t quantity squared. We're simplifying the powers by multiplying the t and the 2 together to get e raised to the 2t power. Then we have plus 1 times 3e to the t plus another 1 times 3e to the t. So that's 3e to the t plus 3e to the t. That becomes plus 6e to the t. And finally, we multiply the 1's together to have a plus 1. For example 2, we want to FOIL out a couple of these factors first, and then we'll multiply by the third. So let's first work on factoring out cx plus d times x minus 1. We have cx times x is cx squared plus dx minus 1cx minus d. And we are multiplying this times x plus 2. We can group some like terms here with the dx minus cx. So we have cx squared plus d minus c times x minus d times x plus 2. And now we can work on foiling this expression here. We'll multiply each of these terms by the x and then multiply them by the 2. So first, cx squared times x, cx cubed, plus d minus cx times x is d minus cx squared, minus dx. Now we multiply everything by 2. We have a 2cx squared plus 2d minus cx minus 2d. Now we can group like terms according to the exponent x. So I have an x cubed, I have a couple of x squareds, a couple of linear x terms, and then finally a constant. So finally, cx cubed plus d minus c plus 2c x squared will turn into a d plus c. We have a plus 2c minus c, so we'll have a d plus c. So d plus cx squared. Then we have a minus dx plus 2d minus cx. This 2d minus a d will be a single 1 times d. So we have plus d minus 2cx minus 2d. That one's fairly involved. Let's take a look at this example 3. Here we want to bring the 3x into the square root. Now, since we have an x minus 1 in the square root, that means x should be greater than or equal to 1. Otherwise, we'll have negatives underneath the square root, which would give us complex numbers, which we're not going to consider. So to bring the 3x inside, we can square 3x and then bring it inside the square root. So this becomes the square root of 9x squared. That was the 3x that we brought into the square root. 3 squared 9, x squared x squared, times the quantity x minus 1. So this can simplify to be the square root of 9x cubed minus 9x squared. Now that we've worked on some distributing, let's try some factoring. Let's factor x squared plus x cubed. I see a common factor of x squared, so we can write this as x squared times 1 plus x. And it's usually easier to think of distributing back through and making sure that we get what we started with, and indeed we do. For the x squared minus 3x plus 2, I notice that I could take an x minus 1 times an x minus 2. Think about foiling. We'd have a minus 1x minus 2x would be minus 3x. Negative 1 times negative 2 is a plus 2. This is indeed the correct factorization. For example 3, it's important to see that we have the difference of two perfect squares. We have x squared squared minus 4 squared. So this factors as x squared minus 4 times x squared plus 4. Once again, if we distribute to expand this out, we'll see that it simplifies to x to the 4th minus 16. X squared plus 4 cannot be factored, but x squared minus 4 can. That's again the difference of two perfect squares. So we could factor one more time, x minus 2 times x plus 2 times x squared plus 4. That's as far as we can factor without using complex numbers. Now for example 4, I see a common factor of x, so I can take out an x times x squared plus x plus 2. And we could think of trying to find a factorization here. We could maybe use the quadratic formula if we don't see a factorization. To try the quadratic formula, we see that we have an a equals 1 x squared, b equals 1 times x, and a c equals 2. So the quadratic formula is negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. And we have a negative 1 plus or minus the square root of 1 squared is 1 minus 4 times a times c. 4ac is 4 times 1 times 2, that is 8, divided by 2a, a is 1. So we divide by 2. Notice that we have the square root of negative 7. We can't take the square root of a negative number since we're not going to consider complex numbers. So since we have the square root of a negative number, we cannot factor here over the real numbers. This b squared minus 4ac is called the discriminant. And if the discriminant is negative, we cannot factor. We call x squared plus x plus 2 an irreducible quadratic. And we'll see these later when we talk about integration using partial fraction decomposition.